In classical mathematics, a formal theory is usually treated as a finished product. You start with a set of axioms, you locate every theorem they can logically prove, and you call that resulting collection a deductive closure. But that static view ignores the mechanics of how those axioms actually work together. Instead of analyzing the final output alone, we can evaluate a theory as a dynamic mathematical space, a productivity field, denoted as V of S, that measures the productive weight of any given combination of axioms. Every possible subtheory exists as a node in a Boolean lattice. Because of the way this lattice is built, it automatically carries its own geometry. It gives us a canonical discrete differential calculus, an intrinsic mathematical structure that we get completely for free, without having to impose an outside framework. Analyzing this lattice moves the focus from the sheer quantity of theorems to the specific mechanics that generate them. Imagine building a theory by adding axioms one by one. The specific sequence in which you introduce them is called a stop permutation. It represents a distinct path of construction through our lattice. Many different paths can lead to the exact same final subset or state of axioms, but when we just look at the final state, we collapse the history of how it was built, throwing away the mathematical information about which individual axioms contributed the most value at each step. To rigorously measure exactly how much information is lost in that collapse, we use a specific metric, axiom synergy curvature, denoted by the Greek letter kappa. Mathematically, kappa is the discrete second derivative across the Boolean cube. It measures the change in productivity when two axioms are introduced together versus when they are introduced separately. This second derivative treats axioms as interacting agents, allowing us to quantify synergy or redundancy using a framework of attributed value. The core object we are studying is no longer a static list of rules. It is the pair V delta, the productivity field, and the discrete geometry that governs it. Let's ground this abstract topology in a computable model. We will use a standard classical propositional logic system containing exactly three axioms, labeled A, B, and C. For this example, we will define our productivity field, V of S, as the total number of distinct theorems we can prove from a given set using 2 logical steps or less. This diagram maps our combinations onto a Boolean cube, with a table outlining the roles. Axiom A states if P, then Q. Axiom B states P. Axiom C states R. If we evaluate their individual productivity, axiom A on its own yields exactly 1 theorem. Axiom B on its own also yields exactly 1. A and B combined yield 3 theorems. This extra theorem, Q, is the direct result of their interaction. Because the combined productivity is greater than the sum of its parts, we have concrete proof of logical synergy that demands quantification. To calculate the exact curvature of that interaction, we zoom in on the paths leading from an empty set to the state containing A and B. There are 2 distinct routes, introducing A then B or B then A. We start by finding the first finite difference. This is the marginal gain in theorems achieved by adding a single axiom as we move along the outer edges of the square. Next, we calculate the second finite difference across the interior face of the square. This is our axiom synergy curvature. The equation subtracts the individual marginal gains from the combined productivity and adds back the baseline. Plugging the theorem counts from our model into the equation gives us 3 minus 1 minus 1 plus 0. The resulting curvature is 1. This curvature of exactly 1 is the precise mathematical measurement of the path dependency in this subtheory. It isolates the exact amount of information lost when you only look at the final set of axioms instead of how they were assembled. We can extrapolate this 3-axiom square into a generalized n-dimensional Boolean cube, representing a theory of any size. When we do, a strict mathematical equivalence emerges. If a theory is completely path-independent, its curvature vanishes to exactly 0 everywhere. A curvature of 0 is entirely equivalent to pure modularity. The reason for this strict equivalence lies in the topology. The Boolean cube is an acyclic space, meaning its cubical cohomology is mathematically trivial in all dimensions of 1 or higher. Because of this triviality, every cocycle on the cube is inherently a coboundary. That means our curvature, the discrete coboundary delta V, is the single unique geometric obstruction to path independence. There is no room in this geometry for hidden third-order structural synergies to lurk undetected. Is kappa equals 0? The theory is perfectly modular, and every axiom acts entirely independently. This geometric perspective maps directly onto cooperative game theory. If we treat the axioms as individual players and the resulting theorems as a shared payout, our productivity field acts exactly as a characteristic function. When we average the first finite difference across every possible path in the lattice, the result is the Shapley value. This gives us the objectively fair portion of credit each individual axiom deserves for the final theory. If we take the second finite difference, our curvature, and average it across those same paths, we derive the Owen interaction index. This isolates the exact credit owed to specific pairs of axioms working together. This table breaks down the hierarchy of finite differences. We have to be precise. Curvature is not the same thing as the pure algebraic interaction coefficient derived from Mobius inversion. Curvature measures local cohological integratability, meaning it inherently bleeds in higher-order data from the upper regions of the lattice. Mobius inversion, represented in the third column, strips that away to isolate the pure combinatorial algebra of a specific subset. By laying out the productivity field over this cube, a single framework simultaneously resolves questions of logical structure, game-theoretic fairness, and algebraic combinatorics. Up to this point, we've only dealt with finite axiom sets, but the geometric structure behaves differently when a theory scales to an infinite number of axioms. In the infinite case, the Boolean lattice shifts into the Scott topology. The finite paths of axiom construction stretch out into continuous monotone chains. In this context, the stop operator adopts a new role. It ceases to be a simple subset selector and becomes a Cauchy convergence criterion. We don't stop observing because the theory has reached a formal halting state. We stop when the marginal gain of adding new axioms, our first finite difference, drops below a predefined mathematical tolerance. For infinite systems, theory construction is not about exhaustive deduction. It is a continuous limit process, defined entirely by mathematical stabilization. Everything we've covered traces back to the fundamental pairing introduced at the beginning, the productivity field, and its discrete difference operator. Crucially, this differential geometry is not an artificial layer imposed on the logic. It is supplied entirely for free by the inherent mathematical structure of the Boolean lattice itself. To understand a formal system, we have to look past the static deductive endpoints. The real mechanics are found in the differential calculus of the paths used to build them. By rigorously quantifying the geometric synergy between axioms, we reveal the algebraic and game-theoretic laws that actually govern how logical truth is constructed.